Hello, welcome back to another Learning Glass session. Today we're going to talk about heat engines, and there is a theoretical limit for heat engines where we have shown in class and other times that if we're going to get some source of energy from a high temperature thermal reservoir, the best you can do is with a Carnot cycle, a special set of processes all at the theoretical limit. And by doing those steps, you can get the most mechanical work out from the cycle for the amount of high temperature energy you put in. So in that Carnot cycle, it operated around a high temperature thermal reservoir and a low temperature thermal reservoir. And engines are nice because you can get a compact size engine where the working fluid goes through a cycle, and because you're going in a cycle, you can get a steady flow of work out in a compact size. So that's why we still use engines. And the problem, though, is the downside is that to keep this cycle going from the initial state to the final state, which is the same, keep on going from the same state in a cycle, you have to lose energy to the surroundings. And in fact, in real engines, most of the energy you get from the high temperature source, the high temperature stage, gets lost to the surroundings. And the Carnot cycle is the best you can do. So if we were to draw this Carnot cycle on a pressure volume diagram, the Carnot cycle, it's characterized by the two thermal reservoirs. And on a PV diagram for ideal gas, we can say that if the ideal gas law applies to this, let's say air or something, some working fluid gas, then on a PV diagram, a line of constant temperature would look like this, where the dependent variable is dependent on V, and if temperature is constant, this line is what it looks like if P equals R, let's call it T hot, over V. So on this PV diagram, all along this line, the temperature is this high temperature of the thermal reservoir. And similarly, this lower temperature here would be the line of constant lower temperature, and it follows a curve like this, 1 over V. So the Carnot cycle, it's characterized by some high temperature state. So in the first state, you take in energy from the high temperature thermal reservoir so it'll be taking in energy by heat transfer from the surroundings to the working fluid. And the special thing about this Carnot cycle is that it's the theoretical limit. What it's saying here is that you're increasing the energy of the working fluid, but the temperature stays constant, even though there's heat transfer coming in. I mean, the temperature stays constant, that's weird, but what's weirder as well is that the source of energy is at the same temperature as the sink of energy. That doesn't happen in real life, but it's a theoretical limit. So all of this is happening at the high temperature TH. It doesn't really work like that in real life, but we can think of that as a theoretical limit. So this would be the first stage, going from high temperature heat transfer to increase the energy, work out, and then increasing the energy by heat transfer. Then what happens is you undergo another power stroke or some expansion to get more work out, and that is an adiabatic isentropic step, where you go another expansion step, but you're going from the high temperature to the low temperature branch. So that would be part of this cycle. Then, let me make this bigger, just for, make this a bigger expansion step here. So let's have it end go to here eventually. Then let's have this go here at this expansion. So it'll go here, and then isentropic expansion to this final volume here from the high temperature branch to the low temperature branch. Then this is a cycle because we can get a nice compact source of mechanical work from this high temperature reservoir. But to keep the cycle going, we have to end up at this state again. Because we started here, we go through a cycle, we want to end there again to keep the cycle going. No one has been able to avoid the fact that to keep this cycle going and make our way back to this state, we have to transfer energy out to the surroundings. It's some energy loss through temperature, heat transfer, at lower temperature than the high temperature reservoir. So the Carnot cycle steps, they do this through another isothermal heat transfer where energy is lost to the surroundings at this low temperature, which is the same thing, same theoretical limits as this. You transfer heat out and the temperature stays constant, which is can happen in some cases, but here, what's weird about this is that you have the same temperature as the surroundings as the system. So, I mean, you're going from transferring heat, you should transfer heat from hot to cold. Here, you're transferring heat from cold to cold, or it should be cold to colder, but here it's cold to cold. So that is a theoretical limit. Then, when we lose that energy to the surroundings, the system compresses to this volume here. Then, to get back to the original state, we undergo an isentropic compression step to get back to state 1. So this is a heat transfer step. So that is the Carnot cycle. And what we're showing here, one characteristic of the Carnot cycle is you're directly operating around the high temperature branch and the low temperature branch, and you're transferring heat from the high temperature source all at TH, losing heat to the surroundings or to the low temperature reservoir at TC. Okay, it turns out that if we're running a heat engine, which we still do, gasoline can be modeled by Otto cycles, diesel engines can be modeled by diesel cycle, jet engines, flying planes can be modeled by Brayton cycle. Electrical power generators burning natural gas can be, for electricity, can be modeled with the Brayton cycle. Coal power plants, nuclear power plants can be modeled with the steam Rankine cycle. These are all heat engines where either through nuclear energy or through burning of fuel, we get a high temperature at some point. That energy, that's where it increases the energy of our working fluid, and then we get some more mechanical work than we get out than we put in. The problem with these, though, is we're always losing energy to the surroundings. So let's show how the Carnot cycle would compare to, let's say, an Otto cycle operating around the same temperatures limits and the same volume limit. So here it's the maximum volume of our Otto cycle and the minimum volume, so this is going to be the Otto cycle down here and corresponds to the same volume limits we had for our Carnot cycle. And then let's draw these same two temperature limits. These are the isotherms, meaning the same temperature all along this line. So this again would be P equals RTH over V. P equals RTC over V. Okay, so the Otto cycle is characterized by, and it happens in the cylinder typically, you have a compression step, then the volume of the piston doesn't change, you just simply keep the piston there, and then you take in energy from the surroundings in the ideal case. Not a real internal combustion engine, it's a little bit different, but in the ideal Otto cycle, you keep the piston there and you take in energy from the surroundings. That increases the temperature, increases the pressure. The difference between the Otto cycle and Carnot cycle is that when you compress, the temperature, so this would be TC here, this is the coldest temperature of the Otto cycle. During the compression stage, it doesn't stay the same temperature. That compression increases the temperature. Even though it's isentropic compression, you still have some increase in temperature. So it will go like a compression line like this. Adiabatic isentropic compression, you'll still increase the temperature from that compression to a higher density and a higher pressure. So that would be after the isentropic compression. Then, if we're operating around the same temperature branch, what you would do is take energy from the surroundings at high temperature. So from either in the real internal combustion engine, you burn a gasoline fuel air mixture. It'll burn and get a high temperature in the ideal case the same volume, but in a real engine it changes a little bit. And in here we're going to do the ideal case where the energy comes in and at constant volume the temperature increases to the hottest temperature of the cycle and the highest pressure of the cycle. So this is how the ideal Otto cycle would look around these same limits. Then you would have your power stroke. But in the ideal Otto cycle, it's isentropic, it's adiabatic, but the temperature still decreases because of this expansion. So you won't stay at the same high temperature. You'll have a lower temperature somewhere like here. So this would be the coldest temperature limit. This would be the highest temperature limit. And so what we're seeing here is that we're mapping out a different set of conditions here. Then for the exhaust-like step, you have to bring the cycle back to its original state, and that requires, we haven't been able to avoid some heat loss out to the surroundings. So that's how the states would look between an Otto cycle. So this is P, V, this is an Otto cycle, ideal Otto. This is an ideal Carnot up here. Okay, so that's what would be the differences. Around the same volume limits and temperature limits, this is how it would map out. You don't keep the same temperatures, and in the Otto cycle, the highest temperature is reached after this heat transfer in, and the lowest temperature is at the initial state before you compress. But there's some differences. There's instead of having two temperature that you operate under, there's 4 different temperatures you operate around. Okay, what about, let's say, the Brayton cycle? So let's see if I can quickly just draw another quick Carnot cycle to compare overlapping in terms of, okay, so this would be another PV. Let's see if I can duplicate this to some extent here. Try to as close as I can. So the Carnot cycle has these isotherms. Brayton cycle, it's not going to follow these isotherms, but we're going to use them for comparison. Then we're going to, let's have this extreme volume here. Okay, so this would be Carnot, and this would be P equals RTH over V, P equals RT cold over volume. Okay? So in the Carnot cycle, we have this heat transfer in, and it causes the volume to increase at the same temperature. Then we have this expansion to our maximum volume. Then we compress and lose some heat to the surroundings. Then we have this compression to get the state back. So this would be the Carnot cycle. Okay. For the Brayton cycle, let's start with the compression step. Trying to remember how the best way. Okay. So, to make this easier to draw for me, the turbine stage of well, let's start from the heat transfer stage. So, in a Brayton cycle, the ideal case is at constant pressure, you take in energy from, let's say, a pressure about here at this minimum density, our maximum density, minimum volume. You take in heat transfer from the surroundings to increase the energy, increase the enthalpy, and what it looks like on a PV diagram is like this. So this would be the isobaric heat transfer at high temperature. And it doesn't stay at TH. This would be the highest temperature here, TH. The state after the combustion or heat transfers mimicking combustion. So either an internal combustion turbine combustor, internal combustion jet engine, which has a combustor, you burn the fuel and that increases the height to the highest temperature of the cycle. Let's say it's branched by this TH here. And that occurs at constant pressure. So here you have the highest temperature, the highest enthalpy, then you're able to get mechanical work in the turbine stage of the turbine engine, and that brings it all the way to the maximum volume. So let's go all the way isentropic, all the way to this step, which I went too far. It is that maximum volume. So it is that maximum volume, but you end somewhere here, not at the lowest temperature. You're not at the lowest temperature. How do you get to the lowest temperature? You have to exhaust out to the surroundings at constant pressure. So this would be the turbine step. This would be the exhaust-like step where you have QC. So take in energy from the high energy source or the internal combustion. You get some mechanical work out from the turbine. Then you either exhaust the burned mixture and you get fresh air in to bring back to the initial state of fresh air. Once you have a fresh air start, you then compress to prepare for the next combustion. So these would be isobaric lines here. So that would be, this line will look like this. So we sweep that line like this, and we don't reach, this is the lowest temperature here. This is something else. This is not on this low temperature line. So that's what a Brayton cycle would look like. So this is Carnot, this would be Brayton. Ideal. Simple, the simplest case. We can make these more complicated and add steps and things like that, but for the simplest ideal case, these are these on the PV diagram, and what they show is some graphical representation where on a PV diagram, this can be the graphical representation of mechanical work, because for an ideal gas or for any fluid, you can find the mechanical work from the integral of P dV. And integrals, mathematically what they are on a graphical, on any 2D space, would be the area under this curve. So here, if we were to call this here state 1, state 2, state 3, this would all be mechanical work out. Why? Because the volume increases. So for the Carnot cycle, the work from 1 to 3 equals the integral from state 1 to state 3 of this pressure volume relationship. And on the graph, it would literally be this area here. But to keep the cycle going, we either transfer heat out, and if the volume change or some mechanical work, and depending on the details, there is some pressure volume that goes in, so it's work in. So if we were to map that out, the work from 3 to 1 equals the integral from 3 to 1 of P dV, and that would look like this curve. So the net work out is, work net out equals 1 3 is out minus work 3 1. So there's more work out because these are higher PVs. There's more that you get out than you put in, and if you were to draw this, it'll be this. Let's draw straight lines down. So this would be the net work out. This the difference between this area and this whole area. It's the work enclosed by this volume. So graphically, if we were to just eyeball this, for the same temperatures, branches, and volume branches on a PV diagram, the typical steps for an Otto cycle and a Brayton cycle, they give you that. Carnot cycle fills out a lot of this area. Brayton cycle, it's a little more obvious the way I drew it. It just depends on the details. We can quantify this more carefully. But Brayton cycle looks a little more obvious. Carnot cycle is a little less obvious, but theoretically, the whole idea is that if you were to do the steps of isothermal heat transfers, isentropic expansions, that will cover the most area possible under these two temperature branches. Otto cycle, it looks a little bit closer, but theoretically it should not be as good as doing this set of steps. So that's one other way of saying that the Carnot cycle will give you the most, so for given TC, TH, V min, V max, Carnot cycle gives most net work out. That's what we want. This is a heat engine. So we want the most mechanical work we can get out. Okay, so we can quantify this, but I'll leave that to you guys as a exercise. And with that, I'll see you guys next time. Thank you.